So I'd like to thank the organisers very much for the kind invitation to speak at this conference. It's really a pleasure to be here, and in fact it's my second conference in Toulouse this summer. So what I'm going to speak about is, as Peter mentioned in his kind introduction, and thank you for that, I'm going to speak about some work that we've done in collaboration with the National Health Service in the UK relating to healthcare-related applications that involve optimization problems where we want to optimize some form of social welfare. That might come from ordinal preferences or from cardinal utilities. So what we're dealing with is two particular types of matching problem. One that arises in the allocation of junior doctors to hospitals, and the other that arises in the allocation of kidney patients to donors, where we want to formulate so-called kidney swaps. So what I'm going to do in this talk is I'm going to outline more about these particular matching problems and the applications behind them. I'm going to then define the underlying theoretical problems and talk about their NP hardness, and then how we can deal with them through constraint and integer programming techniques. I'll then outline some of the computational experience that we've had based on both real data arising from practical matching runs of these problems, and then also computational results based on empirically generated data. So this is joint work with a number of colleagues at Glasgow University, including Rob Irving, Augustine Quinashi, Ian McBride, Greg O'Malley, Patrick Prosser and James Trimble. All of these have been involved at one stage or another. So the talk is going to be split into two parts, and the first part is going to concern junior doctor allocation, and the second part will focus on kidney exchange. So starting with junior doctor allocation, which models the problem involving the assignment of graduating medical students to the first positions in hospitals. In order to become a qualified junior doctor, typically medical students need to undertake some fixed-term period of training in a teaching hospital. So in a number of countries, we have a matching problem based on allocating the junior doctors to hospitals. So applicants, the junior doctors, will typically have a subset of hospitals that they will rank in strict order of preference. There may be many hospitals to select from, but they will decide some subset of those that they find acceptable. Hospitals, likewise, will have an acceptable set of applicants and will rank those in strict order. In a number of countries, these preference lists on both sides of the market are then passed to a trusted third party, sometimes known as a centralized clearinghouse. By economists, we can think of them as a centralized matching scheme, which has the responsibility to construct a matching of applicants to hospitals based on these preference lists. So there are a number of examples of these in countries around the world. Perhaps the largest and best known is the National Resident Matching Program in the United States, which has been in operation since 1952. And it handles the allocation annually of around 30 to 40,000 medical students. And there are counterparts in Canada, Japan, and until recently in Scotland, the Scottish Foundation Allocation Scheme was running, and it handled typically around 750 applicants, choosing from among 50 hospitals. So that's obviously a much smaller application than in the case of the United States. But even with an instance this large, it's still of paramount importance to have some algorithm that performs well in practice. So what might we aim for when it comes to trying to find a good solution? Well, Al Roth, who jointly won the Nobel Prize in Economic Sciences in 2012, argued convincingly that a key property of a matching that should be constructed in a bipartite matching market such as this, where preference lists are on both sides, is a property called stability. And stability ensures that there's no matching where we have an applicant and a hospital who would prefer to be allocated to each other than to stick with their assignments that have been given to them in the matching. If such an applicant and a hospital were to exist, then they could form an arrangement outside of the matching together and undermine its integrity. So we want to avoid that kind of situation by finding what's called a stable matching. So what's the underlying problem model that we're dealing with? It's called the hospital's residence problem, or HR for short. Resident here is primarily a North American term, which just refers to a graduating medical student seeking to become allocated to a hospital. So in this context, we have N1 residents, which are R1 up to RN1, and N2 hospitals, H1 up to HN2. And each hospital has a positive integral capacity, giving us the maximum number of residents that it can take on. Now, residents will rank a subset of available hospitals in strict order of preference, and likewise, hospitals will rank in strict order their applicants. We say that a resident R finds a hospital H acceptable if H appears on R's preference list and R finds H unacceptable otherwise, and we can define acceptability in a similar fashion for hospitals over residents. So a matching in this context is just a set of resident hospital pairs satisfying the following three conditions. Firstly, if a resident R and a hospital H are assigned to one another, then they must find each other acceptable. So we don't send a resident to a hospital not on his or her preference list. Secondly, every resident must appear in at most one pair. And thirdly, no hospital receives more assignees than it has room for. So these are the three properties for a matching. Let's see an example instance of the problem. So here we have an instance of a hospital's residence problem involving 6 residents, and we have 3 hospitals. And each hospital has a capacity of 2 in this toy example. Each resident has been asked to rank 2 of the 3 hospitals in strict order of preference. So for example, R1 prefers H2 to H1 and does not find H3 acceptable. H1, on the other hand, has R1 as its first choice, R3 as its second choice, and does not find R4 acceptable. Right, so what do we want to do in this context? Well, we want to find a stable matching. So a matching is stable if it admits what's called, if it admits no blocking pair. So what's a blocking pair in this context? It's a resident R and hospital H who are not matched together who satisfy the following 3 conditions. Firstly, they find one another acceptable, so they write each other on their preference lists. Secondly, the resident concerned could improve relative to its situation in the matching. Either R is unmatched in the matching and would like to become matched to H, or R prefers H to his or her assigned hospital in the matching. And thirdly, this condition here represents how a hospital could improve, either because it was undersubscribed in the matching and would like to take on an extra resident R, or because it was fully subscribed already but prefers R to the worst resident assigned to it in the matching. So conditions 2 and 3 tell us how a resident and a hospital could simultaneously improve relative to their situations in the matching. We want to avoid that from happening because it would destabilize a matching. So we want to avoid a blocking pair. Here's an example of a stable matching in an instance of the hospital's residence problem. So we've got 6 residents and 3 hospitals, and the matching has been shown directly by being drawn onto the preference list. So for example, R1 is assigned to H2, R2 is assigned to H1, and we can also see the hospital's situation as well. So clearly, because the matching has been drawn directly onto the preference lists, we only have mutually acceptable resident hospital pairs. Also, it's easy to see that each resident has at most 1 hospital, and no hospital has more residents than assignees. Now, why is it stable? Well, if we look at residents R1, R2, and R3, they each have their first choice, so they can't improve, so they can't be involved in a blocking pair. If we look at R4, that resident prefers H2 to its assigned hospital, which is H3, but H2 is fully subscribed and ranks R4 lower down than its worst assignee. So although R4 would like to become assigned to H2 does not have an incentive to cooperate with R4 in a blocking pair. So no blocking pair involving R4 and H2. And by similar reasoning, we can see that R5 can't be involved in the blocking pair with either of the hospitals on its list, and neither can R6. So we have a stable matching, and another way of writing it out is explicitly as a sequence of pairs, and so there are 5 residents matched, so we say that the matching has size 5. It's also possible to see that in a stable matching we have an example where a resident is unmatched, namely R5, and a hospital is undersubscribed, namely H3. So now we have an example instance of the problem with a stable matching, and Gale and Shapley proved in a seminal paper in 1962 that an arbitrary instance of HR always admits a stable matching, and their proof of this was constructive in that they came up with a linear time algorithm which has become known as the Gale-Shapley algorithm for constructing a stable matching. There are many stable matchings for a general instance of the problem, but 2 distinguished stable matchings can be highlighted. The resident optimal stable matching is uniquely and simultaneously best possible for the residents, whilst the hospital optimal stable matching is the optimal counterpart for the other side of the market. Also, the set of stable matchings forms an I-structure, a distributive lattice, with the resident optimal and hospital optimal stable matchings at opposite ends. We also have a nice structural result called the rural hospitals theorem, which is actually a collection of results. It says, firstly, that for a given instance of the hospital's residence problem, the same set of residents are matched and unmatched in all stable matchings. Secondly, each hospital has the same number of assignees in all stable matchings. And thirdly, any hospital that's undersubscribed in one stable matching has exactly the same set of assignees in all stable matchings. So let's just briefly return to this slide here. And we can see that resident R5 is the unlucky resident who's going to be unmatched in all stable matchings. Even if we were to find another one, R5 will be unmatched. And H3 in any other stable matching will also be assigned only resident R4. As a consequence of the rural hospitals theorem, all stable matchings have the same size for the hospital's residence problem. So with that in mind, those are some results for the classical version of the problem. I'm now going to move on to two hard variants of the problem which form the main focus of the new work. So in the hospital's residence problem with ties, we can motivate this problem by observing that in general hospitals might want to express indifference in their preference lists. In general, we can expect residents' preference lists to be short, and therefore it's reasonable to expect that they might be able to rank their acceptable hospitals in strict order. On the other hand, hospitals could have hundreds of applications, and therefore it's reasonable to assume that they might want to express indifference. It might be difficult for them to rank all their applicants in strict order. So we get what's called the hospital's residence problem with ties, in which a hospital can express indifference, as in this example here, where H1 is indifferent between residents R1 and R3, who are represented by the joint, by the brackets, so shown as a tie in position 1 of H1's preference list. They're both strictly preferred to R2, and R2 is strictly preferred to each of the residents R5, R6, and R8, who are also involved in a tie. So what's the definition of stability in the context of HRT? Well, it's exactly the same as before. It's exactly the same as for the HR case, subject to the caveat that we interpret preference as strict preference. So, for example, if a hospital is fully subscribed, then it can't improve unless it strictly prefers some resident to the worst resident assigned to it. It's not enough for the hospital just to be indifferent between its worst resident and a new resident that's trying to move to it. So let's see an example to try to illustrate this. Here we have a larger instance of the hospital's residence problem with couples, with ties rather. We've got 3 hospitals here, and in hospital H2 we have the last 2 residents who are tied, shown by the round brackets. Now let's see a matching of size 5, and let's just have a look briefly at why it's stable. So if we look at R5, this resident is unmatched and would like to become assigned to H2. Hospital H2 is fully subscribed, but is indifferent between the worst resident assigned to it, who is R4, and resident R5. So although R5 would like to become assigned to H2, H2 would not have an incentive to deviate from its assignment and become allocated to R4. Similarly, R5 can't form a blocking pair with H1, and R6 can't form a blocking pair with H1. So we have a stable matching of size 5. Now consider this stable matching here, which has size 6. Why is it stable? Well, let's just consider one potential blocking pair involving R4 and H2. R4 prefers H2 to its assigned hospital, who is H3. But if we look at H2, again, H2 is fully subscribed and indifferent between its worst assignee and R4. So there's no blocking pair involving R4 and H2. So here we have a stable matching of size 6. So this immediately tells us that stable matchings have different sizes for an arbitrary instance of the problem. And what that means is that we have a motivation of the problem of finding a maximum cardinality stable matching, because clearly, if stable matchings can have different sizes, it's of interest to find a stable matching that maximizes the number of applicants who are matched after the first round. If any resident is unmatched after the first round of an algorithm, then clearly they may be disappointed and they may have to then scramble around for places that are left over. The problem of finding a maximum cardinality stable matching we refer to as max HRT, and it turns out that this problem is NP-hard in a number of restricted settings. In a later paper with Rob Irving, we carried out an empirical analysis of both approximation algorithms and heuristics of this problem. And we found that some heuristics that were employed by the Scottish Foundation Allocation Scheme were performing well in relation to approximation algorithms with provable performance guarantees. Also, in more recent work, we have an integer programming model for max HRT, and I'll say more about that later. But before that, I'm going to move on to the second hard variant of the hospital's residence problem, which is again motivated by applications, which involves couples in the problem. So pairs of residents may apply jointly because they want to be matched to geographically close hospitals. They don't want one member of a couple being assigned to one end of the country and the other member of the couple being assigned to completely the opposite end. So couples can apply jointly by providing preference lists based on pairs of hospitals instead of individual hospitals. So the preference list of a couple, RIRJ, typically involves pairs of hospitals of the form HPHQ, where each pair represents the simultaneous assignment of RI to HP and RJ to HQ. And of course, the intuition here is that HP and HQ would typically be hospitals close together, or they may even be the same hospital. So in this context, there are in fact several stability definitions that have been formulated in the literature, and unfortunately there's no single definition that's been agreed upon. But regardless of which definition we adopt, we can define the hospital's residence problem with couples, or HRC for short. And in this context, we can show by example that we might not be able to find a stable matching. And recall that that's by contrast to the classical hospital's residence case, or even the HRT case where ties are in the lists, where a stable matching is guaranteed. Even worse, the problem of deciding whether a stable matching does exist is NP-complete, and again that holds in a number of restricted settings. Even when a stable matching does exist, two stable matchings could have different sizes in an arbitrary instance of the problem. So before saying more about our practical experience related to the hospital's residence problem with couples, I'm going to outline some of the constraint programming approaches that have been taken to dealing with both restrictions and generalizations of the hospital's residence problem. And I'm going to start off with the restriction of the hospital's residence problem in which all hospitals have a capacity of 1. So this is more commonly referred to as the stable marriage problem with incomplete lists, in which men and women are more commonly used to refer to the residents in hospitals respectively. So in a paper in CP01, Ian Gent, Patrick Prosser, myself and others were able to come up with a constraint programming model for the stable managed problem with incomplete lists and show that if we enforce arc consistency in this model, then we get a structure called the GS lists, which stands for the Gale-Shapley lists. These are a set of reduced preference lists that follow if we apply the extended version of the Gale-Shapley algorithm from the men's side and from the women's side subsequently. The Gale-Shapley lists include the full set of stable matchings, and we're able to show that with a suitable value ordering heuristic, we could then get a failure-free enumeration of the entire set of stable matchings. A number of subsequent papers followed up on this and provided alternative models for the stable managed problem with incomplete lists, showing analogous structural properties. For the case where ties can be included in the preference lists, we have the so-called stable managed problem with ties and incomplete lists, or SMTI for short. In a couple of papers in 2002, Ian Gent and Patrick Prosser came up with, again, constraint programming encodings of SMTI. One of these was a SAT encoding, and they gave an empirical analysis showing how these models behaved for randomly generated problem instances. For the stable roommates problem, which is a non-bipartite generalization of SMI, where we have a single set of agents seeking to become matched among themselves, Patrick Prosser a couple of years ago in CPAI-OR came up with, again, a CP model for this and did an empirical study. And in fact, at this conference, Kieran McCreish, James Trimble and Patrick Prosser have a paper about morphing between stable managed and stable roommates, looking at how some structural properties vary as we move from the bipartite to the non-bipartite setting. So that talk is going to be tomorrow morning. Moving to the general hospital's residence case, together with, again, Patrick, Chris Unsworth and Greg O'Malley, we had a constraint programming model for the hospital's residence problem in the CPAI-OR conference in 2007, showing again that arc consistency gives us the so-called GS lists from which we can extract stable matchings. Erinakis in the same year came up with a model for the many-to-many generalization of HR. Now, Ciala and O'Sullivan this year in the CPAIOR conference showed that if we're not interested in establishing a structure as strong as arc consistency, but instead go for a weaker version, namely bounds consistency, then they came up with a faster algorithm than ours for establishing bounds consistency, and were able to again find stable matchings. For the hospital's residence problem with ties, Greg O'Malley in his PhD thesis came up with a constraint programming model. We found that this wasn't especially scalable. For the hospital's residence problem with couples, however, a more recent model turns out to be a bit more scalable, and I'll talk about that in more details on Thursday morning, a talk that is devoted to the hospital's residence problem with couples. But just to give an overview of one of these constraint programming models, I'm going to focus on one of these models for the stable marriage problem with incomplete lists, which comes from a paper in an IJCAI workshop from 2005. So the idea is just to give a flavor of the types of techniques that are used for this family of problems. So let's suppose we're given an instance of the stable marriage problem with incomplete lists. We can just think of this as the hospital's residence problem in which all hospitals have capacity 1. But the residents are more commonly referred to as the men, so let's enumerate those as M1 up to Mn, and the women are going to be called W1 up to Wn. So we have corresponding variables x1 up to xn for the men and y1 up to yn for the women. And the domain of each xi is going to be the set of integers 1, 2 up to the length of mi's preference list, union together with the integer n plus 1, where n plus 1 represents the special case that mi is unmatched. And we have a similar set of values for the domain of yj corresponding to wj. So what does the value xi equal to p mean for p in the range 1 to the length of mi's preference list? It means that intuitively mi is assigned... Oh, okay. Maybe this is a bit more reliable. Okay, thank you. It means that mi is assigned to his p choice woman. And equivalently, right, is that better? Okay, so equivalently, if yj is equal to q, then wj is assigned to her q choice man. Okay, so here we have the set of constraints in this model. So let's suppose that we look at number 1. So this is effectively a family of constraints. So for any I in the range 1 to n, and for any p in the range 1 up to the length of mi's preference list, then let's suppose that the rank of mi and wj in mi's list is p. So wj is the woman who's ranked p in mi's list. And let's suppose that mi has a rank of q in wj's list. So constraint number 1 says that if xi is larger than or equal to p, then yj is less than or equal to q. So in other words, if mi is either unmatched or has a woman ranked p or worse, then wj better be matched to a man in position q or better. So this is to avoid mi and wj being a blocking pair. If mi is unmatched or has a partner worse than wj, then wj better be matched to a man better than mi. Constraint number 4 handles matching. So if mi does not have wj as a partner, then wj does not have mi as a partner. We also have a set of constraints enforcing similar properties for the women, and that helps from a propagation point of view. So if we were to enforce arc consistency in this model, then we get a structure known as the GS lists. Okay, so I'm going to move on now to some of our real-world experience that we've had with the Scottish Foundation Allocation Scheme. So this is a matching scheme that was run by NHS Education for Scotland, and between 1999 to 2012, Rob Irving and I worked in collaboration with NHS Education for Scotland and supplied the algorithms that were used for the annual allocation of applicants to programmes. So applicants and programmes were the terminology that was more commonly referring to the residents and hospitals respectively. So each applicant ranked 10 programmes in strict order of preference, and they had a score that was derived from academic merit and situational judgment tests. And from 2009 onwards, 2 applicants were allowed to apply jointly as a couple. Each programme, on the other hand, had a capacity indicating the maximum number of applicants it could take on, and its preference list was derived from this scoring function involving the applicants. So essentially, all the applicants were ranked according to this uniform master list that was objectively giving them some criterion. Because the master list was derived from relatively coarse-grained scores, it was possible for ties to be involved in the preference lists of the hospitals, because it was certainly possible for 2 applicants to have the same score. So if we have a look at the situation from the point of view of the 2006 to 2008 matching runs, these were modelled and solved using integer programming in this model with Augustine Quinashi in 2014. In this table here, we can see the characteristics for each of these years. So for example, in 2006, there were 759 applicants applying for 53 programs, so there were always more posts than applicants. We can see the size of a maximum cardinality stable matching found by the integer programming technique, and we can compare that with the maximum size of stable matching that was found using the best possible approximation algorithm and heuristic from the paper in 2009, and that's this column here. And finally, we can compare those sizes with the size of the stable matching that was computed by the SFAS algorithm at that time. And finally, the rightmost column gives the time taken for the IP model. So we can see that, for example, in 2008, the SFAS algorithm was doing reasonably well compared to the size of a maximum cardinality stable matching, but in 2006 to 2007, there was some room for improvement. Moving on to some more recent results for the data sets between 2010 to 2012, couples were then involved in an instance, and the couples made up around 5% of all the applicants. So for example, in 2010, there were 20 couples from 734 applicants. What we can again see is the size of a maximum cardinality stable matching that was obtained this time from another integer programming model in a paper with Peter Biro and Ian McBride a couple of years ago. And that's compared against the maximum size of stable matching that was obtained from a heuristic from a paper by Biro et al. In 2011. That's this column here. And finally, we can compare that with the size of stable matching that was obtained by the SFAS algorithm that was employed at that particular time. So again, we can see that the SFAS algorithm was doing reasonably well compared to the size of a maximum cardinality stable matching. In fact, it was hitting an optimal solution in each of the years 2010 and 2012. And unfortunately, we couldn't recreate the data set from 2011 to be able to get the comparison for the integer programming model. But we were able to see, at least for the SFAS algorithm, that it was somewhat less than the size of the stable matching computed by the heuristic. Okay, so looking at how we can scale up these models, well, based on randomly generated instances, we did some calculations empirically, and we could see that the HRT model was able to scale up to instances involving around 600 residents with preference lists of length 5, and 42 hospitals having a total of 600 posts. And we had a tie density in the hospitals list of around 85%. And with that particular tie density, that was reckoned to be among the most difficult family of instances. So we had 100 instances that were run subject to those characteristics, and the timeout limit was set to 5 minutes. 92% of the instances terminated within that time, with the mean runtime being around 3 minutes. So those experiments were highlighted in Augustine Quinashi's thesis. Moving on to the hospital's residence problem with couples model, we were able to scale up to a larger number of residents this time, although this was a different set of experiments where the preference lists were actually varying between lengths 3 and 5. Half of the residents were involved in a couple, and there were 100 hospitals having a total of 1,000 posts, and all preference lists were strictly ordered. This time 1,000 instances were run, and all instances ran to completion, with the mean runtime being approximately 80 seconds, and that was described in more detail by Ian McBride. So the key question then for us going forward is how to cope with larger instances, because clearly these instances are much smaller than for the National Resident Matching Programme, which typically involves more than 30,000 residents per year. So again, constraint programming models can help here, along with perhaps more sophisticated integer programming techniques. Okay, so I'm now going to move on to the second part of the talk. I'm going to leave junior doctor allocation behind and move on to kidney exchange, which involves trying to arrange so-called kidney swaps between donors and patients where the donor is willing but incompatible for the patient. So to give some background behind the application, kidney failure is obviously a very serious illness, and there are two main forms of treatment. Firstly, dialysis, and secondly, transplantation. So dialysis obviously has major lifestyle implications for the patient because typically they have to visit their local dialysis unit several times a week. Transplantation, on the other hand, offers much better long-term survival prospects for the patient. but there's a great shortage of donors. In the United Kingdom, as of 31st of March this year, there were over 5,200 patients on the active transplant list waiting for a deceased donor kidney. The median waiting time for adults was around 2 years, 9 months, and for children it was around 9 months based on patient registrations taken over a 4-year period. Now, kidneys obviously can come from deceased donors, and there were over 2,200 transplants in the UK from deceased donors over a 1-year period up to 31st of March this year. Kidneys, on the other hand, can also come from living donors because, of course, healthy adults have 2 kidneys and can often survive with no lifestyle or health implications with just a single kidney in the long term. And there were over 1,000 transplants from living donors over the same 12-month period, and that represented around 32% of all donations in the UK. But what can complicate living kidney donation is, for example, a blood type incompatibility. A donor of blood type A cannot give a kidney to a patient with blood type B, unless there's some kind of immunosuppressant therapy that's taking place. Another reason for a kidney being rejected by a patient is because of a positive cross-match, sometimes referred to as a tissue type incompatibility. So the source of figures on this slide come from the NHS Blood and Transplant Organ Donation and Transplantation Activity Report 2016. Now, in the UK, prior to the 1st of September 2006, there were limitations on the forms of which living kidney donation could take. In particular, you could only donate a kidney to a patient if there was an emotional connection or a genetic connection between the donor and the patient. Typically, that meant that you could only give a kidney to a blood relative or a spouse. But with the introduction of the Human Tissue Act, there was then a new legal framework which essentially allowed transplants to take place between strangers, and that gave new possibilities for living kidney donation. For example, through paired kidney donation, a patient who has a willing but incompatible donor can effectively swap their donor with that of another patient in a similar position. With altruistic or non-directed donation, an altruistic donor, who is a donor who wants to give a kidney for some special reason, but not for any particular patient in mind, they can donate directly to the deceased donor waiting list, thereby benefiting a single patient, or they can benefit multiple patients by triggering what are called domino paired donation chains, or DPD chains, and I'll say a bit more about those shortly. But I'm going to start off with an example of paired kidney donation. This is an example of a pairwise kidney exchange. Pairwise means that it involves 2 couples, and this is one of the UK's first, which involved a Portsmouth and a Plymouth couple, both south coast of England cities, in 2007. So in Plymouth, there was a father-daughter pair. The father required a kidney. His daughter was a willing donor, but unable to donate because of an incompatible blood type. Meanwhile, in Portsmouth, there was a similar situation involving a husband and wife couple. The wife required a kidney. Her husband was willing to donate a kidney to her, but unable to do so because of a positive cross-match. So what happened was a pairwise kidney exchange where the daughter from the first couple donated one of their kidneys to the wife from the second couple in exchange for her husband donating to the father from the first couple. That meant, obviously, that both patients received a kidney, albeit not from their original intended donor. And it also should be mentioned that neither of these couples had met one another previously. Now, this concept of a pairwise exchange need not be restricted to just 2 couples. We could generalise it to 3 couples, and this is one of the UK's first 3-way exchanges, which took place in early December 2009. And it involved an Aberdonian husband and wife, a Hastings brother and sister, and a St Albans husband and wife. And these arrows represent the direction of travel of the kidneys that formed the cycle of swaps between these 3 couples. So the Aberdonian couple were operated on in the Edinburgh Royal Infirmary, while the 2 English-based couples were operated on in London renal transplantation centres. So these 2 arrows here represented the transshipment of kidneys by plane between Edinburgh and London. Now, it should be mentioned that all of these transplantations and nephrectomies have to happen simultaneously because of the risk of a donor backing out after their corresponding patient has received a kidney. It's not possible in the UK to sign a legally binding contract to enforce someone to donate a human organ, so the only way of getting around this problem is to have all of these operations performed simultaneously. And that obviously has major logistical implications because we have 6 operating theatres and surgical teams that are all coordinating with one another on the same day by telephone. So in a number of countries around the world, there are kidney exchange programs which seek to organise systematically the search for optimal sets of kidney exchanges based on donors and patients on their databases. In the United States, there are several examples of these. One is called the Alliance for Paired Donation, which was pioneered by Al Roth and others. And in 3 papers, together with Sun Metz and Unver, he described some of the theoretical challenges underlying this matching scheme. The National Kidney Registry is a nationwide US program, and another is the United Network for Organ Sharing. All of these schemes involve constructing mainly pairwise and 3-way exchanges, but sometimes even longer exchanges have taken place. Amazingly, a 6-way exchange was carried out in April 2008, and I say amazingly because that necessitated 12 simultaneous operating theatres. There are counterparts in other countries around the world. For example, the Netherlands has the world's longest running national matching scheme for paired kidney donation, and there are counterparts in South Korea and Romania, and in the UK we have the National Living Donor Kidney Sharing Schemes, and we've been working with NHS Blood and Transplant in relation to this since 2007. A characteristic of all of these schemes is that they all want to keep the cycles that are involved in these exchanges as short as possible because of the logistical challenges involved in carrying them out in practice. So what's been our involvement here? Well, we've been interested in modelling the problem and seeing how we can solve it using algorithms that perform well in practice. So what we do is we consider the problem in a directed graph setting. So we have a directed graph D with vertex set V and arc set A, and in this example here we have 3 vertices. So the donors and patients are coalesced into single vertices. So in this case, DI is the willing but incompatible donor for PI. Similarly, we have DJ, PJ, and DK, PK. So the arcs here represent potential compatibilities. So we have an arc from vertex I to vertex J if and only if DI is compatible with PJ. So here we can see the arc showing that DI is compatible with PJ. Also, DJ is compatible with PK, and DK is compatible with PI. So immediately we can see that cycles in the graph correspond to potential exchanges. A 2-cycle here shows a potential for a pairwise exchange in which DI can give to PJ in exchange for DJ giving to PI. We also have a 3-cycle showing that DI could give to PJ in exchange for DJ giving to PK in exchange for DK giving to PI. Now, in the directed graph setting, we can use arc weights to model the potential likelihood of success of the given transplant, or we could model patient priorities. And in a crude way, I've just shown the potential for arc weights by illustrating that arcs can have different thickness. So what might we want to do in this setting? Well, obviously, there are different optimality criteria that we might want to adopt. And perhaps one obvious thing that we might want to do is to maximize the number of transplants. So here we have an example instance of a problem involving 5 donor-patient pairs. And again, we've got compatibilities that are shown between donors and patients. Now, I haven't illustrated arc weights here, but what I have done is I've singled out a cycle, and this cycle here gives us a potential 3-way exchange. So clearly we could have 3 transplants. And this is what we could call a maximal solution, because we can't add on any additional cycle without violating the property that each vertex must be incident to at most 1 selected cycle, because each donor is going to donate at most 1 kidney. Otherwise, we're going to be in trouble. So we also have an alternative solution here where we have 5 donor-patient pairs all being involved in a transplant. So this time we've selected this 2-cycle here and this 3-cycle here. So we've achieved a total of 3 transplants by selecting a different set of cycles. So what are we basically dealing with here? Well, we're dealing with a kind of cycle packing problem where we want to maximize the number of covered vertices that are incident to selected cycles that are vertex disjoint. But not only this, we've got an upper bound on the maximum length of cycle. Each cycle should be of length at most 3. Now, the maximization problem in this setting was shown to be NP-hard by Abraham et al., and it wasn't too difficult to adapt their proof to show that the problem is also difficult to approximate. But approximation algorithms or heuristics are not really applicable in this setting because with an application like this, we only really want to settle for an optimal solution. We don't want to settle for anything less than that. So of course, because of the NP hardness of the problem, we're then going to be in the realm of exponential time algorithms in the worst case. But rather than just trying out all possibilities, obviously constraint and integer programming can help us to try to optimize the search. Before talking about a model that can be used for this problem, I'm just going to illustrate some of the particular challenges that are involved in the UK setting. So three-way exchanges are more risky than pairwise exchanges because they involve 6 people, as opposed to a pairwise exchange that only involves 4. And it only takes one person to become ill for the whole cycle to break down. So we might want to minimize the use of three-way exchanges where possible. So for example, if we could have an optimal solution that found 6 transplants, that it could be made up in 2 different ways, either through 3 pairwise exchanges or through 2 three-way exchanges, then we should prefer the solution on the left-hand side because it has only, it has no three-way exchanges compared to the solution on the right-hand side, which has 2. Another way of mitigating the risk associated with three-way exchanges is to prioritize three-way exchanges that have so-called back arcs. So what's a back arc? It's an arc in the opposite direction to the direction of the 3 cycle. So here's a 3 cycle involving 3 donor-patient pairs, and we have an arc in the opposite direction to the direction of the 3 cycle, and it gives an embedded pairwise exchange involving D2P2 and D3P3. What does this mean? Well, if either D1 or P1 were to become ill and to drop out, then there's still a possibility that the embedded pairwise exchange could proceed. So therefore, we can salvage something from the remains of the three-way exchange, and it's some form of fault tolerance. Something else that is of priority to NHSBT are domino-paired donation chains, or DPD chains. I mentioned that these are triggered by altruistic donors. Altruistic donors want to donate a kidney, but they don't have a particular corresponding recipient in mind. So they could donate directly to the deceased donor waiting list, thereby benefiting a single patient, and there's so many patients on the deceased donor waiting list that there's bound to be an excellent match. Or they could trigger what's called a short chain, in which here A1, for example, donates to P3 in exchange for P3's willing but incompatible donor donating to the deceased donor waiting list. So effectively, 2 patients have been benefited. This, of course, can be extended to longer chains. Here's one involving an additional donor-patient pair in the middle, and the final donor is again donating to the deceased donor waiting list, so we end up with 3 patients potentially being benefited. So how do we model this in practice? Well, it's straightforward because all we need to do is to create a dummy patient for each altruistic donor who is automatically compatible with every non-altruistic donor. And this allows us to close the loop and essentially treat short chains and long chains as 2 cycles and 3 cycles respectively. And here's what the situation looks like in the directed graph. So altruistic donor A1 will be compatible with P3. Here, altruistic donor A2, as before, is compatible with P4, and D4 is compatible with P5. Now we add these dummy arcs, which go back from non-altruistic donors to the dummy patients of altruistic donors. And these allow us to search for 2 cycles and 3 cycles in this augmented directed graph. We should just be careful that at most 1 altruistic donor is selected per cycle. Okay, so I'm now going to talk about an integer programming model that's been used to tackle this problem. And in fact, I'm just going to mention a very basic version of the problem and skate over the various optimality properties that need to be optimized in the UK setting. So the cycle formulation is a so-called integer programming formulation that has been used to good effect in kidney exchange programs, and it was first described by Roth et al. In 2007 and first investigated computationally by Abraham et al. The same year. And what it involves is listing all the possible cycles, which correspond to exchanges, of lengths 2 and 3 in a directed graph. And these are going to be called C1 up to Cm. And we're going to have binary variables, which are going to be x1 up to xm, and each of these variables corresponds to one of these cycles. So xi is going to be equal to 1 if and only if cycle ci is chosen and belongs to an optimal solution. We then have an n times n constraint matrix A, so n is the total number of donor-patient pairs, and recall that m is the total number of 2 and 3 cycles. The I, jth entry of that matrix is 1 if and only if vertex vi is incident to cycle cj. So this constraint matrix is used to enforce the property that each vertex must be incident to at most 1 selected cycle. We then have an n times 1 vector of 1s, which enforces this constraint. And we have a cost vector, which corresponds to exactly what we want to optimize, which might, for example, be the number of transplants. So if we want to optimize the number of transplants, then the JAFE member of that cost vector would be the length of the JAFE cycle, the number of transplants that we would obtain from it. So then the integer program to be solved is to maximize C times X such that AX is less than or equal to B where the XI variables are binary. Here's an example of what this model might look like for this particular graph here. So in this graph, we have 5 donor-patient pairs, so n is equal to 5. So we have 5 rows for our constraint matrix. Now we have 7 2 and 3 cycles. We have 4 2 cycles and 3 3 cycles. If we have a look at a typical 2 cycle, cycle C1 is a 2 cycle involving vertices 1 and 2. And so we have a 1 in rows 1 and 2 of column 1. Cycle C2 is a 2 cycle involving vertices 1 and 3. There it is there. So we have a 1 in rows 1 and 3 of column number 2. Now if we have a look at cycle C5, we have a 1 in rows 1, 4 and 2. We have a 3 cycle involving vertices 1, 4 and 2. So we've enumerated all the 2 and 3 cycles, and we've got our constraint matrix. We've got our 5 times 1 vector of 1s, and we've finally got our cost vector, which gives a contribution of 2 for each 2 cycle and 3 for each 3 cycle. So here's an optimal solution. And in this optimal solution, we've selected cycles C2 and C7. Cycle C2 involves vertices 1 and 3, and cycle C7 involves vertices 2, 5, and 4. So we've got a total of 5 transplants. Let's now turn to some computational experience. So we've been collaborating with NHSBT since 2007, and since 2008, our algorithms have been used for the quarterly matching runs of the matching scheme. So we can see some real-world data from the October 2015 matching run, in which there were 259 donor-patient pairs and 7 altruistic donors, with over 5,000 arcs in the underlying directed graph representing the potential compatibilities. Perhaps a better indication of the complexity of the model comes from the total number of variables. That comes from the total number of 2 cycles and 3 cycles. Of course, these are all overlapping in general. Many of them are overlapping, which means we can't just select them all. In an optimal solution, this particular matching run identified 72 transplants made up of 3 pairwise exchanges, no short chains, 15 three-way exchanges, and 7 long chains. And the total weight was 5,700. Now, unfortunately, not all of the identified transplants lead to surgery because a process known as laboratory cross-matching takes place after an optimal solution has been identified, and that can sometimes identify incompatibilities that hadn't previously been shown up. Also, donors and patients can become too ill for transplant after an optimal solution has been identified before the surgery can take place. Nevertheless, there was a very good conversion in this matching run. 57 transplants went ahead, made up of 2 pairwise exchanges, 1 short chain, which was the remnants of a failed long chain, 11 three-way exchanges, and 6 long chains. Here's a visualization of the July 2015 dataset, which is courtesy of a former project student, Tommy Muggleton, who built a visualizer which shows the underlying directed graph. And we're able to find an optimal solution and then draw it to the edges of the graph to be able to see it better. So there's an example of a 3-way exchange, and we have also a pairwise exchange. Here's a long chain triggered by an altruistic donor. These other vertices in the middle are vertices that correspond to donor-patient pairs not involved in a transplant. And finally, these 2 vertices at the left-hand side are what we call unused altruistic donors. Unused simply means that they didn't belong to a short or long chain, but in practice they would donate directly to the deceased donor waiting list. So to give a summary of the results since the matching scheme begun, I'm just going to mention firstly that altruistic donors were actually entered into the scheme from January 2012, and they were only allowed to trigger short chains at that time up until April 2015, and from that point they were able to trigger long chains as well as short chains. So the total number of transplants that have been identified so far is 949, and the particular components that they're made up from, pairwise exchanges and so on, are shown. The actual number of transplants is 582, again broken down into the different types of exchanges and chains. So that represents a total conversion rate of 65% of the identified transplants actually proceeding to surgery. if we go up to the April 2016 matching run. I haven't gone as far as the most recent matching run, which is July 2016, because we don't know yet the final outcomes from that matching run. As far as the running time of the algorithms are concerned, we're coping well with the data sets from the practical matching runs so far. We can't afford to be complacent because of the challenges that might arise in this particular context in the future. For example, such a challenge, and I'm nearing the end of the talk, so I'm going to mention something that might arise in the future, comes from NEAD chains. So NEAD chains come from so-called non-simultaneous extended altruistic donor chains, and these have been used to very good effect in the United States. They're like domino paired donation chains in that they're triggered by an altruistic donor, and they involve a chain which ends at some donor D3. Now, in the case of a domino paired donation chain, D3 would donate directly to the deceased donor waiting list. But instead, in an NEAD chain, D3 plays the role of a bridge donor, and that means that D3 is held over to the next matching run, where D3 can then play the role of an altruistic donor and trigger another chain segment. And that chain segment itself can have a bridge donor at the end of it, who can be held over to the next matching run to again be an altruistic donor, or at least play the part of an altruistic donor. So in theory, these NEAD chains need never actually terminate, and that's why they're sometimes referred to as never-ending altruistic donor chains. Some of these have been really long. They've involved up to 60 to 90 donors and patients, and they've received quite a lot of publicity in the United States. In this example here, all the chain segments happen to have the same length, but of course that needn't be the case in practice. What's also important to emphasize is that the transplants that are associated with these chains need not take place simultaneously, because in the case of a chain, a donor can donate only after their corresponding patient has received a kidney. And that means that effectively donors can pay it forward. So because there doesn't need to be simultaneity, the chain segments can be longer than, for example, the length of a long chain that's considered in the NHS-BT case at the moment. If we can have longer chain segments, say up to length 6, then that involves an enormous additional complexity, and it could mean that there are potentially hundreds of millions of these types of chain segments in one of these data sets. So future work certainly comes from the potential introduction of these longer chains and the complexity that it would give for tackling the problem. Also, transnational collaboration can give rise to larger pools. As Peter mentioned, we have just kick-started this cost action network on European collaboration on kidney exchange programs, where the idea is to set in motion collaboration between countries, both which have established kidney exchange matching programs and those who either don't yet have kidney exchange programs or at the early stages of setting one up. So certainly this kind of collaboration can give rise to larger pools. Larger pools in general can give the possibility for more and better quality kidney exchanges. Also, the time is ripe for looking at constraint programming models. So far there hasn't been a great deal of work on modelling this problem from a constraint programming point of view. So again, that would be very interesting to try and tackle this from that perspective. Again, there's also the possibility to open up new integer programming formulations and to investigate techniques such as column generation and branch and price, which avoid holding the total model in main memory, and we can tackle larger instances by doing this. So I'd like to finish by just acknowledging collaboration with our colleagues at NHS Blood and Transplant, including Rachel Johnson, Ian Harrison and Matthew Robb, and to finish with a shameless plug for my book, which Peter referred to, which talks about some of the matching problems that I've mentioned so far this morning. And in fact, some of you may have a flyer from the publisher which gives a discount for their promotion, which is valid for CP participants. So thank you very much for your attention. I'll finish there.